Hey everyone, today I want to show you the repair of two Micro ATX motherboard from Asus. Both are Asus ROG Strix B550i gaming models. Those motherboards are great choices for compact gaming desktops as well as home servers. Despite their small size, they are powerful and well equipped. This model features two DDR4 memory slots, PCI Express 4, onboard Wi-Fi, and a built-in sound card. Both of those boards do not post according to the seller's notes. Let's move on to resistance measurements and test power on. Okay, let's measure resistances. What do we have here? For those who are new to our channel, I want to note that measuring resistances on the main power rails is a vital step before powering on to avoid damaging the test CPU. We usually check the 12 volts, 5 volts, and 3.3 volts rail, along with the 5 volts standby and CPU 12 volts line. It's also smart to measure resistance between V-core and CPU 12 volts. They can sometimes short together when a MOSFET blows. Mega ohms. And the V-core 64 ohms, which is quite normal. Okay, let's power it on and see what happens. Since all resistance readings were normal, I moved on to testing the board with power connected. There was no reaction to the power button without the CPU installed, which was expected. AM4 motherboards rely on processor as an essential part of the power on sequence. After installing my Ryzen 3 3200G and the DDR4 memory stick, I finally got a response from the power button. However, the boot process got stuck on the DRAM debug LED. Those motherboards make it quite difficult to see which debug LED is lit, so I used a microscope to confirm that the DRAM LED was indeed the one indicating an issue. Okay, DRAM and steady consumption of 2.5 amps. The DRAM debug LED can light up for several reasons. One common cause is a corrupted BIOS, and another is a broken signal trace between the memory and the CPU. So I decided to use a DDR4 debug card to verify that all the lines have proper connections to the CPU. All connections were good, so there was no need to look for a broken trace in the CPU area. That also meant it was time to move on to step number 2, checking the BIOS. The first thing I want to check is whether the BIOS chip has been desoldered before. Under the microscope, this can be seen by uneven solder on the chip's pins. Well, it doesn't look like someone has desoldered and soldered. It looks like all pads are soldered during the manufacture. I also want to take a look at the chip's marking in case I'll need to remove it and flash it using a programmer later. However, before doing that, I wanted to check if I could flash the BIOS using the flashback feature on this motherboard. Okay, let's try to flash it with the new BIOS. I downloaded the latest BIOS firmware from the Asus website and checked which USB port is used for the flashback procedure. It's usually a dedicated port on the back of the motherboard. In this case, it was the single USB port located next to the flashback button. Then I copied the firmware onto a pre-formatted FAT32 USB stick, ran the renamer tool, which simply renames the BIOS file to the name required by this motherboard's flashback controller, and proceeded with the flashing process. It's also worth noting that this particular motherboard requires an AM4 processor for the flashback procedure, unlike most other motherboards which don't. Shut down your computer, press the BIOS flashback button for 3 seconds until the BIOS flashback. Okay, let's do it. 1, 2, 3. Okay, we have an LED here. It's blinking, so it looks like it's working. I guess it can take about 5 minutes.
5 minutes later.
Okay, and we're done. The LED is no flashing. It's not flashing anymore. So I guess we can power off and remove the USB stick. Let's try to power it on. The BIOS was successfully flashed, so I moved on to powering it up again to see if all our steps had brought us to victory. I really hoped it would work because, honestly, the only things left in my plan were a visual inspection and trying another RAM stick. But my expectations were not met, unfortunately. And I guess no changes, we still have a DRAM LED. And what is wrong with the DRAM? Do you want another slot? And the slot number B is now working. The motherboard still refused to start when the A memory slot was occupied. Tuffet did power on when only the B slot was used. No matter what I tried, nothing helped. I performed a careful visual inspection, but found nothing wrong until I tried a memory stick from another vendor with different timings. And and now it's working. So that's memory dependence. It turns out that Asus Micro ATX boards are quite picky when it comes to memory sticks. They even had a memory compatibility list on the official website. It seems that my chip and buffer test sticks were not fully compatible, but when I installed another set of memory modules, even though they were different from each other, the board finally worked. The motherboard now powers on normally, it exposes DRAM modules in the BIOS and shows all components correctly in Windows Device Manager. So I guess we can say this board was fixed with just a BIOS update and proper memory selection. That was an interesting one. Now let's move on to the second motherboard of the same type and see if we can cure it the same way. I have another board, the same board, but probably without the heatsink for repair. So let this put for cleaning. Let's check resistances. The second board turned out to be identical to the first one. It took me about 3 days to get this one done, and once again I proved to myself that a thorough visual inspection can save a lot of time. This board will lead us into exploring the schematic and board view. Anyway, I won't reveal everything just yet. It's better to show the interesting process of chasing a simple problem, starting from a complex schematic and board view. All resistance readings looked normal, so I moved on to powering it up. Yes, power on, push the button, and we have 400 milliamps, 5 watts. So, okay. It's clear that something goes wrong during the power on sequence. A current draw of around 400 milliamps indicates that V-core hasn't started yet, so I decided to check which other voltages are present and which ones are missing. And it turned out that I found a very important power rail that was missing. What about this voltage? This large coil belongs to VDDQ, the rail that powers the data interface or input-output section of the DRAM chips and some part of the memory controller. So for DDR4 memory it should measure off 1.2 volts. Okay, well, let's disassemble the board and try to look within the thermal camera inside under this PCB. Usually the power on sequence stops because of a damaged resistor or a cracked capacitor that shorts a power good signal to ground. There are plenty of such tiny capacitors gathered around the SIO area, located just under the small dotted board that hold the sound card and the M2 slot. The best way to check for this kind of fault is by using a thermal camera to spot any component that heat up abnormally. During the thermal camera test, I found literally nothing getting unusually hot. The warmest component on the board was the PCH, which is completely normal. So the question was, what's actually causing the problem then? Just to rule it out, I decided to reflash the BIOS. It was unlikely that the BIOS at this stage could prevent the board from booting, but since the flashback feature was working and I already had a flash drive prepared with the latest BIOS from the first board, I decided to give it a try and reflash it anyway. The motherboard still refused to power on and I went back to studying the board view and schematic. I decided to start with the signal I had already confirmed as missing, VDDQ. Tracing the power sequence backward, I was almost stunned by what I discovered and by how well the issue had been hiding from me. According to the board view, the missing VDDQ rail is generated by the PU2000 down converter. This chip has quite a few pins, but my main focus was on its enable pin, because if it's low, the converter won't start and I'd need to trace the circuit that generates the signal. The enable signal comes from pin 33, and after measuring it, I found it was missing. That signal is actually created by another converter, which also supplies the VPP power rail about 2.5 volts for the memory. The VPP rail was present, meaning the converter itself was working, but its power good signal was not. I checked everything in that section, including the feedback circuit. Everything looked fine, so I suspected something else might be pulling the signal down to ground. While examining all the connected components, I finally found a dual MOSFET that had been slightly knocked or pressed. Its pins were shorted together. It was incredibly hard to spot this one. I carefully reflowed the area with hot air and repositioned the MOSFET properly on its pads. Then came the final test, powering on the board to see if we could finally get past that stubborn 400 mA stuck point. Okay, so let's check. Okay, so let's power it on, pushing the power button, and will we have any picture? Okay, switch to CPU, the next VGA, no, DRAM, okay, CPU, this is normal, when the CMOS was clean, okay, VGA, and boot. What about the screen, the post screen? And okay, let's start it again. DRAM, CPU, VGA, and boot. Well, we got a pause screen on this, and we do. Finally. After fixing that tiny, almost invisible MOSFET, the board powered on. The current went past that 400 mA wall, the rails came alive, and the familiar signs of life appeared on the screen. Two identical boards, two completely different stories. One brought back by a simple BIOS update and compatible memory, the other revived by spotting a microscopic fault that could easily go unnoticed. That's what I love about this work. It's never just about fixing electronics, it's about patience, logic, and a bit of intuition. Every repair is a puzzle, every success a quiet moment of victory. If you felt this journey with me, leave a like, it really helps the channel grow. Subscribe if you haven't yet, and stay tuned for more stories like this. Because sometimes, it's not the biggest failure that teaches the most, it's the smallest detail that do. See you in the next one!